Hi everyone, welcome to the channel. So in the last lecture in EM11, we looked at antenna arrays. So what we would like to do is to see how we can simulate them in HFSS, and there are many different ways to do it. So today we look at two methods. I'll leave a couple of links in the description if you want to kind of explore beyond that. But essentially what we want to look at today is two things. So first we want to look at how do you simulate the element factor of an antenna. Right, so we said that an antenna in isolation is different than when an antenna is placed in a periodic environment, right? And when you want to simulate the element factor, you need to place it in a periodic environment. We'll see how to set that up. Then once we do that, then we'll see how we can introduce array factor into the mix and then simulate essentially the radiation pattern of a finite array, where we simulate the element pattern separately, and then we add the element factor separately, and then we add the antenna factor in. And we'll see that that's not exactly 100% accurate. And we also discussed this in the lecture because the element factor and array factor approach assumes that it's exactly periodic, but we know that that's not the case. So at the end, we'll look at a third version, which is in some sense, the most accurate, which actually simulates the entire finite array. Okay. So hopefully you're excited about that. Let's get started. So what I've done here is I've taken a copy of the design we did in EM06 lab and EM08 lab in those two videos, which was just a patch fed by a small lumped port. So we'll start from here since you already have this design. So let me say we'll rename this. I've renamed the main file as well. I'll rename this to A1 element factor. And we want to make a few changes. So I'll delete all of these results. I'm going to redraw them. Next thing I will do is we can delete some of these as well. Don't need them. We'll recreate them. Okay, so we have this big excitation. So let me make everything visible. You can delete this internal box on which we are extracting the fields. Okay, so what we need to do is we need to change the setup a little bit. So I'll delete this. Actually, I'll make this air box invisible. And what I want to do is, since I want this to be a periodic structure, I'm going to make the periodicity equal to lambda over 2. Okay, so to do that, we just have to change the substrate width and the substrate height to lambda over 2 and lambda over 2, right? So that's the spacing now. Or you can also make this a variable, say spacing, and call this lambda over 2, right? So makes it a little easier. Okay, the next thing we want to do is we want to modify the air box a little bit. So we have this air box. We don't really need an air box everywhere because what we want is periodic boundary conditions on the sides. How do we impose that? You delete this air box and just make a manual air box. So I'll make a box, just make a random box, go into create box, and then we'll make this minus substrate width divided by 2, substrate height divided by 2, minus substrate thickness divided by 2, minus the copper thickness. Okay, and this is substrate width, substrate height, and I'll make the total height equal to lambda over 2. And then we saw that the air box and radiation boundary condition, I mean, this would be in the next lecture, which is EM12, where we see that the radiation box has to be at least lambda over 4 to lambda over 2. So lambda over 2 is a good number. Lambda over 2 away from the antenna, right? So that's why the top surface I'm making as lambda over 2 away. So then what I'll do is I will make it transparent so that you can see inside it. And then the reason we don't need radiation down here is because this is a periodic environment. So if you take a really periodic array, infinitely periodic array, then there is no radiation going down, right? It's like the ground plane gets made into an infinite ground plane. Okay. So once we have this kind of box, now we can set periodic boundaries. So I'll select face F, click this, click the opposite face, and say right click, assign boundary coupled lattice pair. Okay, so it's setting up a lattice pair boundary condition. Hit next. So these scan angles determine the periodicity of this lattice pair, right? So ideally, lattice pair boundary conditions, what they can do is that they don't set just the period. So what are they doing, right? So lattice pair boundary condition essentially ensures that the field on this surface and the field on this surface is equal to each other, except for a phase difference between them. Okay, so the magnitudes are equal and you can have a phase difference. That phase difference between them is described by, or is defined by what you set here. And I'll describe how that works. So I'll just say this is phi phase, and set it as a variable. So for now, we'll set it as 0 degrees. Oops, I need to change that. And this should be theta phase. This also I'll set as 0 degrees. Hit OK. And the rest you can leave as default. Okay, so theta and phi, essentially, we haven't done plane waves yet, but if you know plane waves, then essentially theta and phi describe the direction of propagation of a plane wave. So let's assume I set theta to be 45 degrees and phi to be 0 degrees, right? Then there's a plane wave with a k vector that is pointed in that direction defined by theta and phi. And that plane wave defines what the phase difference is between these two surfaces and these two surfaces, because they're all periodic now. Okay, that doesn't really make a lot of sense. That's because we haven't done plane waves yet. But essentially, we can, in a general case, define periodic boundaries with a phase shift between these two. Okay, so we also need to select these two and say couple lattice pair. Then we can leave these as the same. We need them to be the same if you want to have a single plane wave phase difference between the periodic boundaries. Since in this case we are not doing any plane, we just want to have an ideal lattice without any phase shift between the surfaces, an ideal periodic lattice, I'm going to set these values to be 0 and 0. Okay, so now that we have that, we can set the boundary condition here to be radiation, sign boundary, radiation boundary, or you can use PML boundary as we discussed in the previous, in lecture 12, in EM12. But for now, I'll just use radiation boundary. Okay, can go into analysis and make a few changes here as well. So I will set this to be 401 points and then go back to being interpolating. And we'll save just the radiated fields. I don't want to look at the fields inside. That simplifies things a little bit. Okay, say validate, close, and then analyze. So once it's done, we'll take a look at the results. Simulation is done. You can take a look at the results. So we look at S11, which is typical. And you can see it's actually not that well matched anymore. So S11 indeed has changed for making it periodic. And that's pretty significant, right? And the next thing we want to look at is the far field. So I'll introduce a far field setup similar to what we had earlier. Make this 1 degree and this 90 degrees. Okay. And then say create far field report. We can look at the radiation pattern. Far field report, radiation pattern. Now look at the gain pattern for both families. New report. And that's what the pattern looks like, right? So you can look at the max gain and so on and so forth. So I can say add marker 0. It's around 4.7 dB, right? Okay, so in the homework, you would have to plot the difference between the element factor, which is what we've gotten here, here, and the simulation of a patch with without periodic boundaries, right? So if it was just in air, basically. So one interesting question is that, okay, if it's really a periodic structure, then why is there radiation in the back direction, right? Because the ground plane should be essentially infinitely large, and then radiation should not go in the back direction, right? You should get a cutoff here. So the answer to that is that it's just assuming that you have periodic boundaries to solve the fields on this air box. Right? Once it solves the field on the air box, it finds the far field based on those fields. So that doesn't impose the condition of periodicity, right? That just assumes you have some fields on the surface of this box, and from there you're finding the far field. Um, to really impose the fact that there is no back radiation, you need to also add the array factor. So once you add the array factor in, then the field from all the neighboring elements will essentially cancel in the backward direction and you won't have any back radiation. So it's kind of important to understand how HFSS is calculating the far fields, right? It's essentially finding the fields on the surface of this box. Then it's using field equivalence principle, which we looked at in the class, in the previous lectures, and then finding the far field everywhere. That's why you have back radiation. Okay, so once you have this, HFSS actually allows you to fairly easily calculate the total radiation pattern. So I'll make a copy of this. And I'll say this is array pattern, first approach. Okay, so maybe I'll call this A2. So it's the exact same simulation setup. So I'm just going to run it again. You don't have to do that. You can just work with this, but I just wanted to make a separate file of doing that. And then we'll continue once it's done running. Okay, so you can continue. Simulation is done. What I can do is I can go into radiation, say antenna array, and say antenna array setup. Okay, so here you have a few options. You can use custom array if you have a way that in a file in which you've described the array setup. And I'll leave a link in the description below where they actually show how to do that. A lot of the setup actually that I'm doing here is from that video itself, but I wanted to repeat it here just because I want to keep it sort of consistent with the rest of the lectures and with the rest of this video itself, right? So there are other techniques which are not covered in the link in the description. But if you're interested, you can look at that link and see how they do this. But we are interested more in this one, parametric array setup, hit array visibility, and now it shows you what this array factor looks like. So you have stronger excitation in the middle and weaker excitation at the ends. You can change that, of course. So you can go into array geometry, and then so U and V define in which direction you have the periodicity. So here it's a rectangular array. You can make it linear if you like. We'll say design frequency 10 gigahertz. And so the length of the array determines this size, right? And this size. So I want to make it 2.5. So this is in wavelengths, half wavelength spacing. So 2.5 in this, and also half wavelength spacing here. And that determines how many elements, right? There we go. We can also change this a little bit. So let me go back to array setup. You can enforce symmetry to make it a bit faster, but that doesn't really make much difference. So here I have a 6x6 array, right? So I can make it 5x5 to make it symmetric. And then I'll go in here, and this Hamming taper function essentially tapers the amplitude distribution of your array. So we don't want that. We just want a uniform distribution. Okay, and then the scan angle essentially determines in which direction you want the beam to point. So I'll call this phi scan and theta scan, and then hit apply. So we want the beam to point to 0 and 0. Okay. So the nice thing is this is sort of a post-processing approach. Okay, so if you go back in here, you see that the beam pattern has changed, right? Because essentially now we have the array factor included as well. So I can go in here and I can say theta scan 10 degrees. And you can see that it has shifted by 10 degrees in the E plane, right? Sorry, in the H plane because phi is 0. Because phi is 0, it's moving around in the H plane. You can also visualize the 3D pattern. So I'll say insert far field setup, hit OK. It results, create far field report, rectangular plot, dB. I want infinite sphere 2, which is the one we just created. And then hit new report. Oh, sorry. Should not be rectangular plot. It should be 3D polar plot. Last adaptive, infinite sphere 2, dB, new report. Okay, so there we have it. Now what I can do is I can go back here and then say HFSS, fields, plot fields, radiation field, and I want gain plot 2. Apply. We can scale this up to be large. Maybe we can make it size 3. Okay, so that's what the pattern looks like. You can see it's slightly tilted in one direction. So let's see what happens if I increase the number of elements. So let's say I make this 10 by 10. So that's around 20 by 20 array, right? And this would be updated, and you can see it's kind of a sharp radiation pattern, 31 dB of gain. And even here, that's the case. So you can see it's kind of pointing in one direction now, right? So I can also change, I can, if you don't want to look at it in dB, if you want to look at a nice looking beam, you can go back to 3D polar plot and then just plot the gain without dB. You go back to new report. And now it looks like an actual beam, right? You can hardly see the side lobes, so maybe that's not really that useful. Okay, so if you go back here and then I say I want this to be at 45 degrees, it's going to take a few seconds to upload, but now you see that the pattern is in that direction, right? Okay, and of course you can play around with this and see what it looks like. The problem, of course, here is that this is treating this array as ideal, right? Which means that this element factor here and here is the same. But that's not the case because when you have a corner element or an edge element, it doesn't see a periodic boundary condition. It only sees a periodic boundary. It only sees one neighbor. It doesn't see the other neighbor, right? So in fact, the edge elements, you cannot use the same element factor. And that's the approximation that this is making. But of course, this is very fast in terms of simulating because you already simulated it. You just apply the array factor, which is an analytical formula, to get this total radiation pattern. And that's why it's very fast. Right? So what if you want to do it more accurately by including the edge elements as well? Then how do we set it up? So to do that, what I'll do is I'll make a copy of this. We'll use a slightly different tool. So I'm going to say no array setup. Hit OK. So I got rid of the array setup. This part is still the same. I'm not doing anything here. But what I want to do now is I want to change a few things. So we'll go to solution type and say HFSS with hybrid and arrays. Hit OK. So once we have that, we can go back in here. I'll disable sweep. I don't want to look at all frequencies just because it'll take forever to simulate. And then I just want to look at the radiation pattern essentially, not the S11. Excitation is still the same. Boundary conditions are still the same. You have your lattice pairs and the radiation boundary on top. And what we can do is set up an array setup. So I'll say model create array. It'll give you this dialog box. And then for A vector, you just choose the same lattice pairs. And this tells you how big the array is. So 5 by 5. That's the array size. I don't want to have any padding cells. So padding cells essentially create a dummy cell outside your array, so that there's some kind of an air box outside essentially. We don't want to do that. It's not really that important. If you want to be very accurate, you can include that, but it increases your simulation time. Go to active cells and say all active and hit apply. So make it visible and then hit apply. Okay, so that's our array, right? We have this nice big thing. And if you want to, so if you go now into excitations and hit edit sources, you'll see that instead of one source, you have many sources now. Right? You have essentially 25 sources, right, which are all described by this matrix 1, comma 1, and so on. They all have an amplitude excitation of 1 watt, or most of them are 0 watts now, and only one of them is 1 watt. And they all are in phase, so all are 0 degrees. So if you wanted to act like a phased array, then you need to apply some kind of magnitude. Usually, if it's a uniformly excited phased array, all would be the same magnitude. And you would have to apply a phase distribution based on the gradient of phase that you want, right? And we saw that in the lecture on arrays, on how to get that value from the array factor, right? We took the general case and we saw that for a phased array, we have to apply a phase distribution. Luckily for us, HFSS kind of calculates that beforehand or internally, so we can impose that directly. Go to HFSS toolkit and then say finite array beam angle. And it has essentially a calculator that does that. So here I can set data scan, p scan. Don't worry about this phase shift. And this sets the aperture excitation. So basically, if all of them are equal magnitude, this will just be flat. Okay, and this, things like taper and things like that, you don't have to worry about for now. Just say calculate and apply to source. I need to do it. I did not do it. Data scan, fee scan. Let's see. Oh, I see. Yeah, sorry. You don't need to specify it as a variable. You can just set it as 0, 0. Set this to be flat, and then just say calculate and apply. It'll ask you whether you want variables, and then you just hit OK. Done. And now you see it gives you a variable for theta and phi. Right? So we don't really need this anymore because we're not using our array factor approach. Okay, so let's go ahead and simulate this. This will be a long simulation. So the difference between this and actually drawing out your own array is that HFSS basically copies the mesh from just simulating the mesh for a single unit cell and then makes a copy of the mesh everywhere. Right? That's nice because it doesn't have to do an adaptive mesh every single time or for a very large structure. So the meshing is faster, but the simulation is still kind of slow because even after you have the mesh, you still need to simulate. You need to run finite element analysis to actually calculate the fields. Right? So that's the minor difference between actually drawing it out yourself and then making an air box around the whole thing versus using this approach to create the array. There's another approach which includes domain decomposition, which is a little bit faster. And I'll leave a link in the description to a video that explains that as well, if you're interested. But for our purposes, this is good enough for now. Okay, so we'll go ahead and say validate and simulate this. And then once it's done, we'll take a look at the results. Okay, simulation is done. Unfortunately, even after 20 passes, it did not converge. And that's one of the downsides of this approach is that it's very computationally intensive. But even though it did not converge, we can still look at the results. So they're not very accurate, but maybe they're decent. Right, so let's take a look. This is what the radiation pattern looks like, and it looks pretty similar, I would say, to what we had earlier. Right, so we can actually compare them. So I'll go back here. Oh, I need to change this. So we'll go back to 2 and 2. And we also want to go back to 0, 0. Right, okay. So now I can copy the data and compare with this. There we go. So Maybe I'll just look at one plane. So I'll delete this. Oops, I think that deleted both of them. So maybe let's look at just 90 degrees E-plane. Okay, new report. So I'll go back and copy this report in here. Excuse me. Then we can copy this data and then go back to here. Okay. So now essentially I'm comparing the E-plane radiation pattern for the case that had a finite array. Both cases had finite array. One was using the array factor approach, and the other one is using an actual array. Although this did not converge, it's still close enough. Okay, so that's the result. And they look pretty close. At least the beam width looks the same, the null patterns look the same, but back radiation doesn't look that accurate, and so on, right? We did not plot I cannot plot the full frequency response because we didn't simulate it. It would take too long. But you can also actually look at coupling factors. So if I go to model solution report, you can look at all the coupling, right? You can look at S21, basically between multiple ports. So this port and this port, this port and this port, and so on. They're all available here. Okay, what else can you do? We said we can also steer the beam, so we can try that. So let's say I want to steer to 25 degrees. Right, so suppose processing calculation, so it's pretty fast. So you can see that now it's kind of steered to 25 degrees. And we can go into the plot and also look at it there. So in the E-plane, it has kind of gone down because the beam is no longer in the E-plane now, right? The beam is in H-plane. So you can see it's like close to 25 degrees, right? Okay, so if I go back here to the E-plane, and then I say P-scan should be 90 degrees, then we'll get back our beam in the E-plane. There we go. Right, so now it's in the E-plane at 25 degrees. So you can play around with that. You can also look at the excitations and see how they're changing. So if you go out here, then you can look at what the values, how it has applied the phases, right? Okay. Another nice tool to use when we want to do phased array analysis is with such an approach, you can change the port impedance at each terminal. Okay, and for that, you cannot use hybrid model and network. You need to use hybrid terminal network. So hybrid terminal, and I'll leave a link in the description that describes how you can go about doing that. Okay, so that gives you an idea of like, okay, if the port impedances are not the same or one element has started failing, then you can put a short circuit or an open circuit port here and then see how the pattern changes. So that's also a useful tool. Okay, so we've kind of seen, just to summarize, we've seen how to simulate the element factor. We've seen from element factor how to apply an array factor to look at the total radiation pattern and how to steer the beam. We also looked at how to do it more realistically without making the element factor approximation, which is to have a finite array of this size. And we looked at how to steer the beam in this case as well. So I would actually encourage you to look at what S11 looks like at different ports. So what is S11, S22, S33, and so on. And you'll see that for the middle port, it's a little different than for the edge elements. Again, that's because the environment of the edge element is different. So it is really a different antenna in some sense, right, out here. Right. So with that, probably we can stop here. This is a good demonstration, I would say, of simulating arrays and phased arrays and so on and so forth. There are other topics in phased arrays. This doesn't complete everything. So there is something called scan blindness. There is also a way to simulate that in HFSS. It's an interesting topic. It's very practical when you have large phased arrays with more than lambda over 2 spacing. To simulate that, we need to use Floquet ports, which we haven't discussed yet, the theory behind Floquet ports. So that's why I haven't really not presenting it here. But maybe in a future video, we'll discuss how to simulate scan blindness. And there are also other topics in phased arrays that are also very relevant. So this is sort of an introduction to phased array analysis and simulation. Okay, thank you so much. I will see you in the next one.